My name is Ferdinand Gruber and I present Bringing Compiling Databases to Risk Architectures, a joint work with Maximilian Bandle, Alexis Engelke, Jana Gicheva and Thomas Neumann. Let's first talk about the beginning of the current era of code generation. All started with the paper Efficiently Compiling Efficient Query Plans for Modern Hardware in the year 2011. At that time, modern hardware mostly meant x86. In the year 2011, ARMv7 was the current ARM standard, an architecture that even has harder times to support sequential consistency efficiently. Also, ARMv8, the basis for all nowadays ARM processors you know, wasn't even announced yet. To be more precise, the ARM processors available at that time were at the power level of Raspberry Pis, so not the target audience for database systems. However, more than 10 years have passed and many systems adopted query compilation because of the high performance and its flexibility. Also, the server segment and hardware market changed. Powerful ARM processors are now available on the desktop and mobile world with Apple's powerful M-series processors. On the server side, you can either buy Ampere Alta CPUs or rent Amazon's homemade Graviton CPUs in the cloud. On top of that, there's the RISC-V architecture. RISC-V allows you to extend your own CPUs and extension sets and also work on your own CPU designs for your needs. So, compiling for modern hardware nowadays should also meet compiling for ARM. But how do we compile code in databases in general? To answer this question, we did a design space analysis. Which approaches are used currently in the community? How do we get from query to an internal representation and then to machine code? How do these approaches integrate in the system? And how can we assess these approaches? We set a set of metrics therefore. So we looked at latency, how fast does code generation work currently with the approaches, what is the throughput you can expect from one approach, so the performance you get out of it, and the ease of use, how difficult it is to implement a specific code generation approach in your database system. The first and most simple approach is just using programming languages. Your database system is written C or C++, so it's a very good and narrow idea to translate your queries using these two languages. You just generate a query program using code templates or code snippets, put it into GCC or Clang, and then can call the compiler-generated code. Most of you know that C++ compilation is not the fastest thing in the world. However, you can expect a high throughput because you can rely on more than 20 years of compiler optimizations and the work of the compiler community. Also, the ease of use is quite good because you do not have to burden yourself with the underlyings of architecture-specific details or compiler design. Nonetheless, going from your internal representation to a C or C++ program is not always that easy. Therefore, database systems like LegoBase or Euler added an intermediate step here. Instead of directly generate a C or C++ program, you add a high-level language between your internal representation, for example Scala or Euler. This makes code generation a little bit easier because it's not that complex to lower from your high-level constructs to low-level constructs. Of course, this makes latency a little bit worse because you add an intermediate step here. But you can nearly expect the same throughput as with the first approach, using only a C or C++. To address the latency problems, other systems like Hyper directly generate compiler IR programs. So they skip the front-end part of modern compilers. All this parsing and syntactic parsing stuff. This is faster, of course, because it saves some time, and you can nearly expect the same amount of throughput, because all modern compiler optimizations are applied on this level, on the IR level of compilers. Of course, it's a little bit more complex to generate compiler IR programs instead of C programs, but this is still very easy doable. However, there's a third approach that is inspired by the web browser community with the customized code generators for the JavaScript engines. Instead of using existing compiler frameworks and compilation stacks, we implement our own new compiler stack that is explicitly meant to translate our internal representation to our target architecture. This is of course a very fast solution because we do not do unnecessary translation steps. Also, you can expect high throughput because you really control the complete compilation domain here and optimize for your specific problem, your specific database system. Nonetheless, the ease of use is quite low because you really need sophisticated knowledge about the machine code architecture you want to support, and also you need knowledge about compiler construction, for example. However, all these approaches are currently used in the community and well researched for x86. So we want to go to ARM now. How do we do this? We use therefore Umbra. Umbra is a database system that uses the internal representation called Umbra-IR. Umbra supports all of the presented compilation approaches. So we can lower Umbra-IR to C, going over GCC to machine code. We can directly go over the LLVM framework for code generation, or we can use our own custom code generator for x86 called Flying Start that was already published. Just for the sake of completeness, Umbra also has a virtual machine backend with interpretation, but that does not generate code, so we skip it out here. So this is published and well tested on x86. So how does the way to ARM look like? For our C and LLVM backend, that's quite easy. Remove architecture-specific things like SSE or AVX, and then adjust some flags that are may not needed on one architecture. The rest is the compiler's job. Of course, this assumes that it are not using undefined behavior, but because we are here on the VLDB, this should not be a problem anyway. However, this is not possible for customized code generators. So you cannot just change a flag and get ARM code out of our x86 code editor that we implemented. So we have to implement a new compiler backend here for our database systems. We did it and we call it FireARM. This sounds very easy because we already did it for x86, but it's quite challenging in some points going from x86 to ARM. We want to give you a short overview here now about these challenges. The first and major thing is you're going from a strongly consistent ordering model for processor to a weakly ordering consistency model. What does ordering model mean in general? It's the order other processes in the system see writes. So this can affect database systems that work with many threads in parallel on large machines. On the left-hand side, you see all x86 instructions that you need to interact with memory in all strengths and orderings. On the right-hand side, you see just a small output of the available ARM instructions to access memory and control the ordering of your instruction or your load or store. You see this quite much, and ARM gives you a very high flexibility to control what you really want on the load or store operation. But however, ARM also needs this flexibility because it gets much of its performance out of its ability to freely reorder writes on loads in its execution engine. Going from an x86 code generator to an ARM code generator and just translating your x86 instructions with a matching ARM equivalent is not a good idea. Because most of the time x86 has a much higher guarantees for example, memory operations, so you choose a too strong ARM instruction and lose performance. For example, only an LDR instruction is needed in some case, and you would translate it with an LDAR instructions, and you would lose half of your performance. So if you do not know what level of ordering you need in some part of your pipeline, this is the first thing you have to consider and find out. The second problem and the second challenge is instruction selection. Instruction selection is very important for code generators. First, it has to be low latency for our system, for our FireARM, because otherwise we could use LLVM in the first place. Second, the sequence of generated instructions has to be very good because code quality is directly coupled to throughput in a database system. So what's different? First, immediates. x86 nearly supports all immediate sizes in all instructions. You can freely encode anything. On ARM, that's not possible. You're limited in the size for immediates. The size that is supported is even instruction dependent, and it even is dependent on instruction if it's a signed or unsigned immediate supported. Second thing is memory and how you access it. On x86, nearly any instruction can access memory, so you are very free and very easy to generate code. On ARM, you always need specific load and store instructions. You even have to differentiate between aligned and unaligned accesses to memory. So the sequence of load and store instructions that you, for example, generate for a tight loop in your pipeline decides the code quality and the throughput because, for example, a bad sequence leads to stalls. Also affecting the memory is the topic of atomics. On x86, you do not see atomics for loads anyway because some of instructions are sequentially consistent. And if you really need a barrier, for example, for some specific problems, then you use the MFENT instruction. On ARM, you have a more complicated barrier system because most instructions or things only guarantee a half barrier that is only accessible to from one side but not from the other. Also, on x86, atomics are supported for unaligned data. That is not the case for ARM. So this can affect, for example, your internal data structures and the layout. And also, if you have to generate code for atomic operations on ARM, there are different ARM feature extension sets. For example, the LD8L instruction is not available on ARM v8.1, so instead of just using this one instruction, you have to generate a complete loop with different instructions. So this can complicate the code generation phase because you have to know for which processors I really want to generate code, what is supported and what not. However, for FireArm we overcome all of these challenges and we solved the strict alignment, the complex atomics, the problems with the fixed encoding size, the limited the support for immediates, and even some problems with the low-bit arithmetic. And we think we got incredible results out of it. We want to show you now. So the first thing is we did benchmarks. We benchmarked all available compilation approaches, C using LLVM, using customized code generators with x86 and ARM, and even the virtual machine backend in Umbra. Therefore, we used the TPCH benchmark on 9 different systems, consisting out of ARM and x86 consumer hardware, as well as high-end ARM and x86 server hardware. So, how does a benchmark look like? Here, on the x-axis, you will always see the latency, right side is lower. On the y-axis, you see the throughput, so how many tuples does the generated code get through per second. The place of interest, where do you want to be? Of course, the top right corner, lowest possible latency for code generation with the highest achievable throughput. On the downside here, you see the legend with the different backends and the color codes. So, looking at server hardware. On the left-hand side, you see Graviton 3 processor as an ARM processor, modern one. On the right-hand side, you see the EPYC 7713 and modern x86 processor on the server segment. As you can see, the benchmarks nearly look the same. You see the same patterns for performance. Our customized code generators, Flying Start and FireArm, generate code in the same order of magnitude than the virtual machine backend that don't even have to generate machine code. Also, they are more than an order of magnitude faster than LLVM code generation, even without optimizations applied, and multiple orders of magnitude faster than code generation using the GCC backend and the C programming language. As you can also see, the throughput that you get out of our customized code generators on ARM as well as on x86 is very high and comparable to sophisticated compiler frameworks. As you may notice, the Graviton 3 is a little bit faster here than the EPYC processor. This is not the features of ARM alone, but also of the available memory. The Graviton 3 already uses DDR5 memory, while the EPYC processor still uses DDR4 memory, and Umbra is a memory-bound system, so a higher bandwidth leads to higher performance. So, to summarize this. ARM for compiling databases, all code generations approaches work very well, and it's a good idea. If you have a programming language backend or use compiler Rs, you can expect a fast porting process without major problems and nearly the same performance than on your existing x86 systems. If you have a low latency custom code generator, then you can also expect low latency code generation with high throughput that is comparable to your existing x86 solution. So no problems going from x86 to ARM. You can even expect the same performance or even better one. However, using the RISC ecosystem or going there leads up to some questions. For example, you can ask yourself if you optimize for specific vendor extensions from one CPU design or one another, or if you want to support specific extension sets in general from the ARM feature set. You can also ask, do you want to support new rising architectures like RISC-V and the subparts? And that's a little bit sad, but it's more difficult to get high performance hardware on the ARM or RISC-V ecosystem than buying just a new x86 server. You even rent some from the vendor, or you are very limited in the thing you can buy. However, going to ARM definitely works out well because you can rely on this energy efficient and very powerful processors that are more and more available nowadays. Thank you.